Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy news journalist for over 20 years. This is the question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops into your brain, just write it down. I'll gather them up and I'll answer them here. And I also do this show live every Monday at 5 p.m. Pacific time. So if you want to come and ask your questions live with me, you can, just every Monday at 5. Now, last time we had the code words. You'll see the code word showing up as we do the questions. And these are, of course, the your votes for the questions that you thought were the best. And that gives us a chance to give a shout out to the person who asked the question. So this week, the most voted was for Hans Majid. What does it take to get high-speed internet to Mars? So congratulations, Hans. I hope everyone loved your question, and hopefully, again, I hope my answer was acceptable. So when you're watching this video, just go ahead and put in the code word for the question that you think is the best, and then that will act as a vote in the comments, and we will announce the winner each week. Have you ever wondered what goes in behind the scenes at Universe Today? I'm doing an interview series with the entire team. Every one of the writers, producers, video creators, everyone behind the scenes. So we've interviewed Anton. I've now done an interview with Nancy Graziano and now Nancy Atkinson, who is our senior editor. So if you want to learn more about Nancy Atkinson, go and check that out. These are all on our Patreon feed, but they're public. And so you can just go and listen to the interviews with everybody on the team. We'll just keep going until we run out of team members, but it's going to take a while. All right, let's get into the questions. Andrew Geber. If we could have an Earth-sized telescope to image a black hole, will it be possible in the near future to have a 2 AU-sized telescope, for example, by depositing a bunch of telescopes from a starship behind and in front of the Earth around the orbit of the Sun, or is that not how things work? So what you're describing is this idea of an interferometer, and we've talked quite a bit about the interferometer that was used for the Event Horizon telescope, and this is where astronomers located telescopes around the world, big radio telescopes, and then use those acting in concert to produce a virtual telescope the size of planet Earth. And all these telescopes worked. They produced an image. Imagine you had a radio telescope the size of planet Earth. And that's why we got such a high resolution image of the supermassive black hole at the heart of the Milky Way and at M87. And again, this number just boggles my mind that it is the size of a donut on the moon. So if you took a donut, put it on the moon, and observed it from Earth, that is how big this object is that they're taking a look at. And this technique called interferometry is where you are able to combine the light from multiple telescopes. And the capability of the telescope is defined by the distance between the telescopes, the resolution. And so if you have a telescope on one side of the Earth and a telescope on the other side of the Earth, it is the equivalent of a telescope the size of the Earth in terms of resolution. But it is not the size of the Earth in terms of brightness, of sensitivity. And so it can view very bright objects like supermassive black hole event horizons, but not very dim objects that are, imagine some planet orbiting another star, which is going to be very dim. So if you have something bright that you want to look at, you want to build an interferometer. So could you scale this up? Could you put a radio telescope on one side of the solar system of Earth's orbit, and then another on the other side of Earth's orbit of the solar system, and then have them record images of a black hole? And the answer is yes, you could. And it's probably within our technology at this point. You'd have both of these incredible radio telescopes recording their data, and then they would be beaming all this data back to Earth, which would take a long time. Like when the Event Horizon telescope was gathering its images, in some cases, it made more sense. It was faster to just take your hard drives, put them on an aircraft, fly them to the place where you were combining all the data. But theoretically, you could transmit this data back to Earth, and you would now have a telescope that is the size of 1 AU, the size of the solar system in terms of resolution, but not in terms of brightness, of faintness, of sensitivity. So again, you need to look at something very bright. But that's for the radio spectrum. And the reason why the radio spectrum is easier, the way these interferometers work, and they're very complicated, but the gist is that you have to line up the telescopes down to the wavefront. And so It literally, imagine photons are particles and waves. And so as one wave of a photon is passing through the Earth, you want the two telescopes to capture it at the same time. And so they're observing it exactly at the same time. And the only way to do that with a radio telescope is you just record everything. And then but also using really high precision, like atomic clocks. And then after the fact, you on computer line up the observations between the two so that you match up when the observations were made to the precise fraction of a second. And then you get this virtual telescope between the two. As the wavelength gets smaller, in other words, as you shift into the infrared, as you shift into the visible light, this gets trickier and trickier, because how do you record video from two telescopes that are really far apart and then combine them down to the point where you've got wavelengths that are, say, 500 nanometers, which is very small. And then when you've been recording for some enormous amount of time. And so trying to be able to do that kind of thing after the fact is probably going to be impossible with our current technology. And so the only way that you could theoretically do it is if you do it in real time. In other words, if you have two telescopes that are apart and they are observing the same object, but they're also communicating with each other, and they're essentially managing their distance away from each other to the point that they are observing the exact same wavefront of this object that's coming towards them. And this idea has been proposed. There's actually a proposal of the terrestrial planet finder, and this was going to be a space telescope, maybe 4 telescopes flying in formation, acting like a single telescope based on the separation in between them. And people have also proposed that you could set up one telescope on one side of the sun, one telescope on the other side of the sun, maybe at the L4, L5, and the L3 point. And they form this giant equilateral triangle. And then you could get their timings right, and they would be able to communicate with each other and act like a single telescope of that size. But the orbit of the Earth isn't circular. It is elliptical. And so you're not going to get this perfect orbit. The spacecraft literally have to be able to maintain themselves within a fraction of a millimeter to be able to act like a single telescope. So it's probably going to be a long time before we're able to do this. Now, the concrete plan is going to be the LISA, the Laser Interferometer Space Antenna, which is going to be looking for gravitational waves. And it's going to be flying in formation, acting like an interferometer, and really testing out a lot of this technology. So the same kind of technology that's going into LISA to detect gravitational waves could theoretically be used to develop a visual telescope, maybe something that's in the optical range, but is flying in formation and acting like an interferometer. So the idea of it being the size of the solar system is ambitious, probably beyond our technology, but definitely space-based interferometers are the future. Serban Nicolau. Is the orientation of the Sagittarius A black hole due to a previous merger with another black hole in an engulfed galaxy? One of the really interesting discoveries made with the observations of the supermassive black hole at the heart of the Milky Way, Sag A star, was that the black hole's rotation, its orientation, didn't line up with the orientation of the Milky Way. It's sort of rolled over on its side and roughly pointing towards us, like off by 30 degrees. And this was quite a surprise. Astronomers weren't sure. They thought it might be lined up with the Milky Way. Maybe it was off axis. And so how did a supermassive black hole, something with 4.1 million times the mass of the sun, end up not on axis? How did it get rolled over? And the answer seems to be through mergers. And this sort of goes back to the fundamental question of where supermassive black holes come from in the first place. Did they form from some giant cloud of gas and dust that just collapsed into one enormous supermassive black hole? Or did they form through the mergers of smaller black holes? And if you've got a black hole that's kicked over on its side, then that probably happened because two black holes collided, or maybe a third one, and you got this event that rolled it over on the side. When we look here in the solar system, we see that Uranus is rolled over on its side. And we see that Venus has been flipped over 180 degrees and is rotating backwards compared to the other planets in the solar system. So this adds some line of evidence to the possibility that the supermassive black hole at the heart of the Milky Way is the result of many mergers with other black holes that got it into its current position. Echo 12. I'm a data analyst working in astronomy in the UK. One thing I struggle to explain to the layman is how we age stars. How would I best explain this? Thanks. I don't blame you. Figuring out the age of stars is actually a very inexact science in the realm of astronomy. Astronomers are not super happy with how well they're able to calculate the current age of stars. So there's a couple of ways to go about it. So the one is if you've got a star in a cluster, then you're on easy street, because the theory goes that all of the stars in a cluster all formed together. And so if you've got, say, a globular cluster or even some large open star cluster, you can look at all the stars, and then you look for the kind of star that is probably the oldest. And the way this works is astronomers know that the more massive a star is, the shorter its life is going to be. So if you've got a star like Betelgeuse, it's only going to survive a few million years and then it's going to explode as a supernova. And so you look at this star cluster and you say, oh, there's none of the stars that will detonate after 10 million years. Oh, there's none that'll detonate after 20 million years. Oh, but there are some that would take 50 million years to detonate. So the star cluster could be 50 million years old and no less. And so then you've got the one star you want to try and figure out how old it is. Well, now you know how old the star cluster is, and you can roughly guess the age of the star. But if you don't have a star cluster, then it gets really tricky, because stars don't show their age. So you can't just observe a star and go, oh, it is this color. Oh, it's this mass. Oh, it's spinning this speed. Oh, it's got these chemicals in its outer atmosphere. That tells me how old that star is, like carbon dating. You can't do that. And so there's a couple of ways to do it that are fairly rough, and a new technique that's actually pretty accurate. So the main method, and this is going to sound kind of hilarious, is there is the Hertzsprung-Russell diagram. Essentially, astronomers have built this map of how stars move through the main sequence phase and how they begin their life and how they end their life. And based on the color of the star, you can roughly tell what kind of a star it is and what its overall age is going to be. And you can get a super rough to within multiple billions of years of how old the star is. Like our sun, if you were seeing it from afar, you might think it could be anywhere from a couple of billion years old to 8-9 billion years old. Like, as long as it's not in the protostar phase or in the dead stage, it's somewhere in between. And that is really unsatisfying. And astronomers once thought that maybe you could tell by the rotation speed of a star, because in theory, stars slow down over time as they get older. But there's been plenty of examples where that's not the case. Maybe the planets can spin up the star. Maybe interactions with other stars can spin it back up. So that doesn't seem to be a reliable method. So there's a new technique called astroseismology. And this is only just a couple of years old, like maybe 3 years old. And it was developed using data from the Kepler Space Telescope. And what astronomers did was they looked at stars that were changing in brightness, not because they had planets necessarily passing in front of them, but Kepler was staring at this one field of stars for an incredibly long period of time and was able to map the brightness of stars with incredible precision. And by doing so, it was able to just see how the star was flickering. And that gave it a sense of what kinds of internal processes were going on in the star. And then based on our knowledge of the sun and how the sun has internal processes, we know how old the sun is, they were able to compare that and get a sense with more accuracy of how old stars are. So now all you have to do is have a mission like Kepler, carefully watch one star for a long period of time, detect the ripples coming off of the star, and that allows you to give a sense of how old the star is. But it is not easy. It is a very, very tricky technical issue, and astronomers would love an easier way to figure out the ages of stars. Matthew Stevens. Fraser, would it be possible to create a large telescope like the overwhelmingly large telescope by using a collection of small mirrors and focusing them onto a single mirror as opposed to one single large mirror? So this is related to the idea of interferometers, and so I won't sort of go over the whole interferometer part again, but imagine you've got, I don't know, some space telescope that is made of 18 separate hexagonal mirrors all arrayed together, and each one of them is independently flexing back and forth, being able to target itself, and they combine all of their light onto a single secondary mirror, and then that mirror bounces in and you're able to produce an image. And I'm describing the James Webb Space Telescope. And that is how it works. That it really is actually a collection of 18 separate space telescopes flying in formation with the ability to change the angle, the position of these mirrors so carefully that they can combine the telescopes, combine the wavefront into a single image. And that's why James Webb is able to act as a single telescope. And there have been other examples here on Earth, and there's a few that are being built right now. The biggest one is called the Giant Magellan Telescope, and it's going to be 7 mirrors, all sort of 6 around and 1 in the center, but they're all circular mirrors. And the same thing, they're all going to be aligned with such precision that they act like a single mirror. But you could have them be far apart from each other as well. Now, not like an interferometer. So in other words, they're not going to act like a single telescope, but they could be separated by a random distance. And so you could have, say, 10 different telescopes all just flying around together in a rough formation. And you wouldn't get a telescope as big as the distance of the telescopes, but you would get a telescope as powerful as the combined surface area of all of those telescopes. So in other words, it would be if you had 10 telescopes that were all the same size, they would act like 10 times one telescope if you combined all their light and aimed it at a certain location. Not to the nanometer precision, but roughly. And so there's also been thinking about flying fairly rough space telescopes in formation and combining the light crudely so that you get the added gathering power of all of those telescopes. And the cool thing about this idea is you could then fly more telescopes. You could send up 10 more and then send up 10 more. And each time you're just adding more and more telescopes to the formation, your light gathering capability of this instrument increases. You can always split it up and have 2 groups of telescopes looking in 2 different directions, or they could all work together to look at one object. And it's a pretty exciting idea. I like it a lot, and I'm hoping that someone will try this out in space in the future. RJQ, when building the Uranus orbiter, why not just build 2 and send the other to Neptune, Voyager style? Well, that would be awesome. I mean, you should always just build 2 of everything that you do. And the Voyagers are like an anomaly when you think about it, that they sent 2 spacecraft that were almost identical to do the same rough job, although they ended up going on different trajectories in the end. But it's amazing the foresight to create. And we had that with the Pioneers, and we had that with some of the Mariner spacecraft, and we haven't seen the exact same thing. We've obviously had Curiosity and Perseverance, which are similar, but not twins of each other. I would love for them to do if they do send a Uranus mission, to also make a copy and send a Neptune mission as well. I would even be willing to, I mean, obviously it's not my decision, but to have less capability, but get this comparison of the 2 planets simultaneously would be really exciting. You would have to follow different trajectories, but you could use gravitational assists from the giant planets in different ways, and you could decrease the time it takes to get out to the outer solar system. So it just comes down to budget. NASA only has a set amount of budget for its planetary science, and they've defined their priority as going to Uranus, probably because it's closer. Like, it's just so much extra time to go all the way out to Neptune if you can get out to Uranus, and you're going to answer a lot of the same questions. So I guess that's why. More questions in a second, but first I'd like to thank our patrons: Jan Fushman, Paul Thompson, Just Askin, Sandre Evertson, Peter Black, John Falconer, and the rest of our 1,029 patrons for their generous support. Want our videos with no ads? Join our community at patreon.com/universetoday. And I'll also remove all of the ads from Universe Today website for life. Sean Karen, why do white dwarf stars explode when they get to 1.4 times the mass of the sun? So that special number, the 1.4 times the mass of the sun, is known as the Chandrasekhar limit. And it was calculated by an astrophysicist named Chandrasekhar quite a long time ago. And the gist of it is that when you look at, say, a white dwarf star, the dead husk of a star like the sun, it is mostly made of the the ash that was created in the star throughout its lifetime. And so you've got at the core of our sun right now, the sun is turning hydrogen into helium, and eventually it'll run out of hydrogen in its core. It'll start turning helium into heavier elements like carbon, and then the star will run out of fuel. It'll expand as a red giant and then blow off all its outer layers, and you'll be left with this dead core of the star. And it'll be mostly carbon with helium and a little bit of other elements around it, and then it'll just cool down to the background temperature of the universe. But if the sun was in a binary system with another star and it was able to feed off of that star, then it would be adding material to the outside of the star. And once it reaches 1.4 times the mass of the sun, essentially the star is held in balance. The gravity is pulling it inward, and the atomic bonds that are between the various atoms are pushing back against. Sort of the same reason why you don't fall through your chair, right? The chair is pushing back against you. But when you hit that 1.4 times the mass of the sun, the inward gravity overcomes the force of the atoms, and the star is able to collapse in on itself. And then that is actually a very explosive process. And so it then detonates as a supernova and is completely destroyed. And so that is the number that if you just keep adding material bit by bit, it's the straw that broke the camel's back. Cheryl, Texas, where is Voyager currently? There's 2 Voyager spacecraft. So Voyager 1, which is the more distant spacecraft, is currently about 21 light hours away from the Earth. And so it takes light 21 hours, actually almost 22 hours, to get to Voyager 1. And then if Voyager 1 wants to send a message back home, it takes another 21.6 hours to get back to us. So if you want to communicate, send a message like, "Hi, Voyager, how you doing?" To get your response back is almost 2 days, which is kind of mind-bending that humanity has sent an object that far away. If you want it in some other numbers, it's 23 billion kilometers away, but 0.00246 light years. So still a fraction of a light year, but still very far. Epic Curious. Could this or some future meteor storm damage or destroy a lot of our satellites? No, not really. The people don't realize, but the Earth is already in a cosmic shooting gallery. About 100 tons of debris hit the Earth every single day and are absorbed by the planet. They hit the atmosphere. And so satellites, as they just spend hours, days, weeks, years outside the atmosphere of the Earth, they have the potential to get pelted by small pieces of debris, micrometeorites. And it happens all the time. You know, when you look at the solar panels of the International Space Station, you can see little dings all through it where little pieces of space debris or particles ran into it. But the bigger risk is not chunks of comets broken up or little pieces of dust left over from the solar system. The big risk is the human space junk. All of the satellites that we're sending up into space that have the potential to collide with each other and release more and more debris. Astronomers are tracking at this point now tens of thousands of pieces of stuff in space. Some are actively functioning satellites, some are dead satellites, some are pieces of satellites, and they are able to track them with a lot of precision, and they know there's just a ton of material up there. And that's really what satellites have to worry about, not stuff, natural debris in the solar system. Purine. Hey Fraser, how far would aliens be able to tell if there's life on Earth to justify sending a probe or traveling here, assuming they have the exact same technology and are 100% like us? I was going to go into all kinds of cool science fiction ideas, and then you said the exact same technology as us. And so if there were aliens living on the closest star system to us, Proxima Centauri, just 4.26 light years away from us, they wouldn't know we're here. They wouldn't even be able to detect the existence of the Earth orbiting around the sun because the sun is too bright. And if the Earth was perfectly lined up and went right in front of the sun, then they would be able to detect the dimming of the light from the sun, and they would be able to know that there is a planet, an Earth-sized planet, orbiting within the habitable zone of the star. But that's pretty much all well, they would then be able to maybe sense the atmosphere of the planet and get a sense that there is water vapor, oxygen, nitrogen, carbon dioxide, and some other gases in the atmosphere of the Earth. They wouldn't be able to hear any of our radio signals. They wouldn't be able to see any of our structures, any of our space infrastructure. And even if they could see those gases in the atmosphere of the Earth, they wouldn't know for sure whether it was intelligent civilization or whether it was just natural product of volcanism or something like that. And so we are not ready. We really don't have the technology right now to know if there are aliens in other star systems. It's still going to take us a few. There's a lot of missions in the works right now, new technologies, new missions that are going to be launching in the next decade. The European Extremely Large Telescope, which is going to be able to potentially directly image Earth-sized worlds orbiting around sun-like stars. But we are still, I would say, 20 years. Like if we went into the future 20 years, then a civilization would be able to, with that kind of technology, would learn quite a lot about us. But we're just not there yet, which is kind of sad. Now, if they had incredible science fiction technology, then they would be able to learn quite a lot about us. If they were within 100 light years of us, they would be able to detect the emissions from our radio broadcasts and our television broadcasts. If they were in a few hundred light years of us, they'd be able to detect the carbon dioxide emissions and pollution from our technology. Even if they were halfway across the galaxy, they would be able to detect just the existence of life on Earth because of how dramatically it's changed the atmosphere of our planet. But it would require some very careful observations. They'd have to really know and be able to see that there's plants and be able to detect how they're reflecting light and the gases they're giving off into the atmosphere and so on. But yeah, no. So even aliens right next door with our technology wouldn't even know we're here. Sunny Vegas, has anyone built a 1G spaceship to simulate gravity, and will it be easier to live on than Mars? Nobody has built a 1G spacecraft to simulate gravity in space. There's been the only test that I know of to even slightly test the idea of using centripetal force to simulate gravity is they spun up the Gemini spacecraft. They had two spacecraft on a tether and they had them go around and they got a slight force that was going outward. They could detect, but it was very, very slow. And so what you really want is you want something that is rotating fast enough that if you're inside of it, you are experiencing 1G of essentially artificial gravity. And that would help deal with a lot of the problems of spaceflight. And you're sort of imagining, if you just want like a ring that is able to give you 1G of gravity, it's actually pretty big. It's in the hundreds of meters across. To have a big ring that's rotating, it takes a minute to rotate once and you would experience 1G. But it doesn't have to be that big. It can actually be very small. It's just that it'll be very uncomfortable. People have proposed tiny little centrifuges that would fit inside, say, a Falcon 9 fairing, just 5 meters across. It wouldn't have to be very big. It would just be super uncomfortable. You'd sit inside of it and it would spin very, very quickly. It would simulate 1G of gravity. You would try to hold back the vomit while you sat inside of it, feeling very uncomfortable, but you would be experiencing artificial gravity. And so maybe you could spend some amount of time, 2 hours a day in the spinner, and that would help you minimize the effect of microgravity on your body. But this experiment has still not been done. There was a proposal to add a new module to the space station called Nautilus X, and it was never actually built. There's been ideas to take the Nautilus X and put it on the Lunar Gateway, but I don't think that's really moved forward either. So right now, nobody is testing out artificial gravity in space. And you're probably wondering, why? Why not? And the reason is just not a priority. That we know how to keep humans in space for a year more. When you think about astronaut Scott Kelly, He spent a year in space showing what happens to the human body, and he was exercising every day. He was doing everything he could to minimize the impact of being in microgravity. And when he came back down, he was weak, but he was able to walk, and he was able to recover within a few weeks and be strong again. And so when you think about the kinds of missions that we're going to do, missions to Mars, you're going to spend, say, 9 months going to Mars. You're going to spend a few months on the surface and then 9 months back, 2 years at the most. We think that we can handle that in terms of having your body not go into any serious health effects. It's being longer in space that nobody has really developed a solution for. And so once that becomes a priority, then you can imagine some of these experiments finally happening. Would it be easier to live in artificial gravity than on Mars? Maybe. I mean, again, we don't know what the impact of 35% gravity has on the human body for long periods of time. 2 years, 3 years, 5 years. Can human beings gestate in low gravity? Can you give birth to a healthy baby in that kind of gravity? Will children grow up properly? We don't know the answer to any of these questions. And so anybody who is planning to send, say, settlers to Mars without having a really good answer to this question is going to be conducting a science experiment on human beings with possible catastrophic results. And so we do need to have these long-term tests done in microgravity where you can spin up the space station, test different levels of gravity, and figure out exactly what is the minimum amount of gravity required for a human being to thrive. So stay tuned for that science, or the just live experiment on human beings. David Waka, do you have any tips to make stargazing more inviting to others? Any darkness-friendly games you have done? My favorite way to do outreach for skywatching is to do sidewalk astronomy. And that's where you go and you take your telescope and you go out to some public space when planets are in the sky, and you set up your telescope and you just stand there. And people will show up. They will ask you what you're doing, and you'll say, oh, I'm looking at Saturn. Do you want to take a look? And they'll look through your telescope and they will have their minds blown. They will not believe what it is they're looking at. They think you're faking it, but you're just showing them Saturn, and then you show them Jupiter, and you will have if it's a busy place, you'll have a lineup of people waiting to look through your telescope. It is so much fun, and just a chance to interact with people and hear their excitement about space. It's funny, like, for all of the issues and arguments and disagreements that people have politically, philosophically, everybody loves space. And so it's something that we can really come together about. And I love doing sidewalk astronomy. And so if you want to sort of interact with more people and share your love of space, get that telescope, stand out on the street corner, invite people to take a look through the eyepiece, and you will make some friends and you will make some new converts to the hobby of amateur astronomy. Vevar, how is it possible to orbit around the Lagrange point? There's no mass at the Lagrange point. Shouldn't an object just be stationary at the Lagrange point, not orbit it? So Lagrange points are places of gravitational stability. And in theory, if you just had the sun with the Earth orbiting around the sun in a perfect circle, then you would have the 5 Lagrange points that were organized around the Earth and the sun. And they would truly be points. There would be one point in between the Earth and the sun. There would be one point on the other side of the sun. There would be one point on the other side of the Earth. And there would be one point before and after the Earth's orbit. They would be points. And if you could perch a spacecraft at exactly that point, then it would just sit there. But they're not points. They are zones, because the Earth's orbit around the sun is an ellipse. It's not a perfect circle. It ranges by several million kilometers. Not only that, but there's the interaction of the other objects in the solar system. You've got the gravity coming from the moon. You've got the gravity coming from Jupiter, from Saturn. Earth isn't a perfect sphere. It's an oblate spheroid. So you've got all of these different factors that work together to turn what could be points into blobby areas where you are roughly in a balance point of gravity. But you have to be able to sort of as the Earth is going around the sun, where this gravitational zone is going to be sort of changes. And so you set your spacecraft up so that it is orbiting around this region, inside this region. And in fact, James Webb is going to have to be able to fire its thrusters about once a month to put itself back into this zone as it sort of continues to go around the Earth. There's no place that it could just be and always remain at the L1, L2, or L3 Lagrange point. Now, L4 and L5 are stable. They're gravitational wells. So if you can get down into the zone and then you can sort of find an orbit inside that area, then you'll remain in there forever. But with L2, where James Webb is, for example, it is unstable. And so James Webb is always trying to drift away out of this zone, thanks to all the interactions of all the planets and the sun and the Earth and the moon and all that. Landon Runseval. Hey, $20 patron here. Are there any plans for return mission to Pluto or the Kuiper Belt in general? If not, should there be? Thank you for becoming a patron. I really appreciate it. Are there any plans to go back to Pluto? Officially, no. But Alan Stern, the principal investigator of the New Horizons mission, which of course did the flyby of Pluto, is really interested in sending an orbiter to Pluto and has developed proposals for it, is building a team, is putting this in front of NASA and anyone who will listen. And I've talked to him in the past, and he feels like there's a really good science case to be made to go back to Pluto. I agree with him. I mean, Pluto is incredible. There's so much additional science, and not just a flyby. Let's get a lander, an orbiter, a rover. Can you imagine a rover roving around the frozen nitrogen glaciers on Pluto? That would be amazing. Yes, please. But right now, currently, as I'm recording this episode, no mission has been greenlit to actually go that. The other mission that's being considered is what's called the interstellar mission. And this is an idea to send a mission out into interstellar space. So roughly, say, where the Voyagers are and beyond, but to do it more quickly, and a way to see how the environment of the Milky Way matches or interacts with the sun, solar wind, and try and get a sense of where's the line between the solar system and space, interstellar space itself. And so maybe it could do a flyby of Pluto as it flies out in that area, but my guess is it's going to have a totally different science package on board. But maybe you could like drop an orbiter or send a sub probe with it. Anyway, so right now there are no plans, but I would love for there to be plans. And, you know, if you want, I can have Alan Stern come back and we can spend a whole hour with him talking about how much he'd love to see a mission going back to Pluto. All right, those were all the questions that we had time for this week. Thank you, everyone who asked them, both in the YouTube chat, but also all the people who showed up live to ask me, to hammer me with questions on Monday. So again, we do this every Monday at 5 p.m. Pacific time, and there will be a link to next week's live show somewhere around here on my channel. So come and join the live show. All right, we'll see you next week. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber, Nancy Graziano, and Anton Poznikov.